very welcome. This is Wireless Future. I'm Erik Larsson, and I'm here as always with my colleague Emil Björnsson. Hello, Emil.
Hello, Erik. It's been a while since we were talking.
It's been a while indeed. I think we did have a break.
Yeah.
From recording. Life and work came in between, but now we are back. And
I guess people working with 6G research in Europe might guess that it could, for example, have to do with all of the calls for big projects that has been the last few months.
It's very possible indeed. In any case, it feels good to be back in the recording studio and smell the fresh air.
Exactly.
Studio air.
And we are planning for a few episodes now before the summer, so this should not be the only one that you will find if you're subscribed to the podcast.
Indeed. So today I think, Emil, is episode 29, isn't it?
It is. So we are soon approaching 30.
That's amazing. 29, that's a prime number. That'll happen less and less frequently, I think. And with that, I mean, it's almost anniversary, right? I mean, and the second anniversary, in fact, approaching us in the fall this year. So the intention today is to discuss sixth generation mobile systems, 6G, and specifically to talk about 6 technologies, or at least say technology trends that are emerging for 6G. So among these trends, Emil, do you have any favorites?
I think it's always easy to sort of get stuck in the things that you know and look for evolutions of those ones. So I mean, different kinds of multi-antenna evolutions is what I primarily look at in my everyday research. But then it's also sort of the thing that when MIMO is out there everywhere, we could also use it as a starting platform to do a lot of other things. So that's why there's so many other things now that interest me as well.
Yeah, absolutely. I mean, I'm also sort of a bit of a MIMO guy, right? So I tend to think MIMO, distributed MIMO, and MIMO in different forms, obviously. But maybe we should start somewhere else today. So how about we start to talk about semantic communications?
Yeah.
Do you want to kick this off? I mean, what is this thing?
Yes, exactly. So I was planning to say a little bit what it is, and then I think we can discuss what could be the good things and potentially the what would be the potential showstoppers, for example, because of course whenever we are working on a new standard with ideas, some things make it into there and some things are not ready enough or doesn't become as promising. So I think for everything that we are working on, it could lead to one of the other cases. But semantics. So I guess in general, semantics means that if you have a text, then the words are there, but the meaning of the words is sort of the semantics. So if you have a textbook, if you just take all the words and you randomize the order, then you lose the semantics, but the content is still there in terms of the words. So what has that to do with communications? Well, typically it's not about only communicating words, but also a meaning. And those meanings should lead to some actions, or we will use the communication output for something. And
Yeah, no, I mean, certainly. But, I mean, why don't you just take this text, right, and you compress it using your favorite gzip or whatever algorithm, and then you encode it using your favorite channel code and transmit it, right?
Yeah, so I think the first thing that people say that is working in this research area is that we would like to go beyond what Shannon was proposing, with the idea that if you read his first paper from 1948, he says that essentially, I don't care about semantics. I just want to have a message. It doesn't matter how we generated it. The message should be transferred to the other side, and we should decode it, and we are done with it. And then,
so message here means you start with a finite set, although it might be very large, obviously, but a finite set of messages that you could conceive of, and then you pick one of them and encode it, right?
Yeah, and then the design is sort of based on to minimize the risk that we are confusing two messages, rather than minimizing the risk that we make the wrong decision in the end based on the message that we are getting. But I think you have a fair point that, I mean, within the Shannon theory, there is all the kind of things about source coding, where you try to compress the source so it conveys the original message, but in a condensed manner as possible. And I think the semantic communication is meant to go beyond that by compressing things even more to only convey the things that are important for what you want to do. So if, for example, a classical mobile phone, when I was studying sort of signal processing in my master, we talked about that the audio encoder is sort of modeling how the voice sounds like, so what frequencies are used, and then you make a model of parametric model of that, and you encode the audio based on that, and everything that is not mapping with that one, the residual, you are compressing it very hard, so you have a lossy encoding of those things, and that is a way of making things more efficient on a statistical level based on that the sounds look like this and that. But I think here the idea with semantic communication is to go far beyond that, not only encode the voice, but also think about what is actually said in the voice, and how should those kind of messages be described in a more efficient manner.
So, I mean, in a way, it's like a very sophisticated form of source coding then, right? Isn't it?
Yeah. So in a way, it is... it's a source coding, and I guess the idea that we should combine this with the communication channel. So maybe we should view it as a joint source and channel coding 2.0 or something like that.
So that would presumably be data-driven in some ways. So you'd have some algorithm that learns from experience, right? Not necessarily relying on an explicit statistical model like in Shannon theory. Is that the reasonable way of thinking of it?
I think when you go beyond the clean Shannon theory, people start to suggest different alternative metrics, and what it often boils down to is that, okay, you have the communication channel, and then you have what they call a semantic channel between the transmitter and receiver, where everyone have a perception of the world and about the task that we want to achieve, and hopefully those perceptions are the same ones, so that we can use this pre-knowledge in order to transfer the meanings more important in a better way. And how would you obtain those things? Well, probably through machine learning, as you were saying.
Yeah, so is it like, I mean, rather than sending across now, I mean, we are recording this through a video call, right? And I see you in real time on my screen here. But rather than sending this bit stream of video across the system, we just send a string stating something to the effect that, well, here is Emil Björnsson, and he's like a couple of months older than he was last time we recorded, and he's wearing the same blue T-shirt that he always does in the podcast.
Exactly.
That would be like 100 bits rather than a million or something, right? Is that like a way of understanding this vision?
Exactly, that could be one way of transferring this type of thing. So you have the audio, you have the video, they are sort of two representation of the same kind of messages, and then instead of sending the actual video stream, you could perhaps have an avatar of me that is sort of regenerating the same thing, and it's might with advanced machine learning look all exactly the same as in the previous podcast. It's just that now my lips are moving based on a new message, for example. So I guess that is one part of it that you could imagine.
Yeah, I mean, it's a cool thing, right? But would this be useful, like in practice? I mean, is it that the savings in bits here are really important in the end, you think? Or what would be like the use cases? Why? I mean, if you really ask the question sharply, I guess it's like, who and when would, I mean, who would want and when would someone want to pay for this technology, right? When would the savings in bit load or transmission, bits per second, be significant enough that it makes a difference?
Yeah, and I think this is really a valid point when it comes to the weaknesses here, that we need to find this kind of really convincing cases. And in addition to what you said, I think there is also the risk that there are so many different tasks we would like to achieve, and each one of them would need a different type of semantic encoding and decoding, and do we get so many of them that we will have to store a lot of things, and we will have to learn a lot of things, and eventually the overhead from doing this is sort of removing the benefits from actually being efficient.
And there is also the energy efficiency aspect, right? I mean, maybe you can make a case, do you save some, I don't know, joule by transmitting fewer bits, but then you need to take into consideration how much training that these methods are going to require. So you need like tons of data, and you need to process all this data. So I guess future will tell, right? But maybe some convincing applications will emerge.
Yeah, and even if you look at the hardware side, and we are using all this kind of source coding methods, for example, for video. There is a number of different standards, and if you agree upon a standard, you can then build a circuit that can hardware accelerate that standard, so it becomes very efficient to decode the video that you are getting. But can you do the same thing if you're training everything, maybe with newer networks? And the last thing, we have been talking for a while about quality of experience, which is to be some kind of metric about how you're perceiving the quality of your communication that goes beyond just how many bits per second are you getting, or what is the mean squared error in your received signal or something like that. And it often boils down to that it's hard to actually optimize this kind of metric. So I think there are big challenges, but that's also good for researchers.
Indeed. All right, so where do we go next, Emil?
So I remember that in the previous podcast I've been talking a lot about distributed and cell-free MIMO, and I was thinking maybe I can ask you this time then, what is this from your perspective, and what would this be about?
DMIMO. I mean, so first, I mean, we did touch that upon that in the podcast in earlier episodes. In a way, I guess it's maybe a little bit of like your pet and my pet. But that said, there's also a case to be made. I think that it's the single most important technology for 6G for the physical layer. And as the audience probably already knows, DMIMO is all about building like MIMO-equipped access points that are distributed. Could be indoors, like in form of antenna panels that sit on the walls or the ceiling or someplace, or it could be outdoors. I mean, in the form of MIMO access points or base stations on towers or on the facade of buildings, or integrated into some other structures. Or even like natural objects could be hidden maybe up in a tree somewhere and just made aesthetically so it looks like nobody could really from a distance at least tell that it's anything artificial or man-made that's put up there. And from the comm theory viewpoint, I mean, the idea here is that obviously within each one of the access points or base stations there are multiple antennas that operate coherently together, phase coherently together, but that these different access points that are also spread out geographically, that in turn they would also operate phase coherently together, right? I mean, is that a fair description, you think, also, Emil?
Yeah, I think that is a fair description. Then I sort of also get the feeling that, didn't we talk about this in like 2008, 9, 10, around that time where I did my PhD. We also talked about sort of distributed MIMO. Then the terms were called network MIMO. Sometimes they were called coordinated multipoint. So what is the difference here from your perspective?
Yeah, so I mean, the idea of making wireless base stations or even wireless MIMO base stations operate phase coherently together is absolutely not new, right? I mean, this has been around for at least 10 years, as you suggested. I think more, 15, maybe 20 years even. Now, the reason that modern DMIMO, which is currently being developed, will work, whereas these like older incarnations of the topic, network MIMO, comp, joint transmission, I'm sure there are many other names as well, they didn't really work. I think the reasons are twofold, really. Number one is that DMIMO should rely on time division duplexing and reciprocity to get the channel state information. So that means the access point measuring uplink pilots sent by the terminals in every coherence blocks. Every time the channel has had the chance even of changing substantially, the terminals will send pilots anew, and these access points will all listen, and based on these received pilots they will obtain channel state information which is timely and accurate, and that channel state information will in turn be used both for processing of uplink data signals and for beamforming of downlink data signals. This is horribly important. I mean, if you think of it, if anything in the environment, I mean, if one of the terminals or any object that contributes significantly to the scattering of the radio frequency waves moves more than half a wavelength, then the channel state information is outdated. And the key here really to make MIMO in general and DMIMO in particular work is that the network needs accurate channel state information that facilitates the use of all these fancy algorithms that we have, right? Like zero forcing beamforming and so forth, that shoots power very accurately in space and makes sure to place like spatial nulls where there's supposed to be no interference transmitted and all that. So I think number one is to use to rely on uplink pilots and reciprocity and time division duplexing to get accurate channel state information, both for the uplink and the downlink.
Yeah, if I can comment on that part, then I mean, the whole idea, the concept of this have, of course, also been around for a long time. I think when I started working out this, we also had the TDD reciprocity in mind. Then I think the problem had for a long time been that, yeah, you could do this in TDD, but all the bands we are using is FDD. And then also when it comes to standardization, we want the system to work the same in TDD and FDD, and then you can't do it anyway. So it's sort of now with 5G we have the opportunity, and 6G.
Yeah, that's a good point. I mean, indeed, there are like spectrum political aspects here, right? That a lot of bands were allocated for FDD and so forth. I think there's also just flat out the pure educational aspect, in the sense that now more and more folks realize the superiority of exploiting reciprocity and operating in TDD. And there's been this lingering misconception, I think, in the community that, it will work to use some code books to quantize the channel state information and rely on some sort of, air quotes, line of sight propagation model where, I mean, these textbook cartoons, right, where you see a uniform linear array in free space, and then you see beams like nicely drawn, like ellipsoidal kind of shapes. But now the thing is, reality doesn't look like that. Not even to start with, most of the time you aren't even much of the time you might not even be in the far field. But even if you're in the far field, the beams don't look like this because of a variety of reasons. One is that we'll always have significant multipath, and we'll also have like backscattering from structures that hold the antenna. We'll have mutual coupling and all sorts of things. So all these like geometric textbook cartoonish models of grids of beams and all that are rather poor representations of reality. And the simplest and best way of just getting away from that whole paradigm is to say, let's just estimate the channel impulse response, unstructured, relying on uplink pilots, and then we measure these, we make sure that we have good enough signal to noise ratio on these pilots, and we make sure that we have little enough like contamination on the pilot channels, which means like don't reuse the pilots too often and so forth, and then measure these channel responses and just use them without imposing like any prior assumptions from some textbook model on what the linear array looks like or anything, right?
Yeah, and so, the dangerous thing there is that there are certain cases, of course, like one user, a very line of sight dominant millimeter wave channel where these textbook things are accurate, but as soon as you are trying to serve multiple users and you have a more complex scenario, then it breaks down. So it's sort of dangerous when you just make measurements and design things for the simplest case, and then it doesn't work in other cases.
No, certainly. I mean, if you take a uniform linear array, constructed the right way, you put it in an anechoic chamber, and then you make sure you are in the far field and measure, you'll see pretty much this textbook van der Monde array response, right? There's no question, but the point is the reality is very much different from what you get in this anechoic chamber with highly calibrated and so forth. Yeah, but back to your...
I think you had the second main
point,
thing,
yes. Right? No, I think the second point is also the fact that modern DMIMO will rely on an excess of service antennas over the number of data streams that are multiplexed simultaneously, or over the number of like terminals that we serve at the same time, right? Which gives us, in a way, it's like, well, we have, because of all the service antennas that we have at all the access points collectively taken, right? they will offer us so many spatial degrees of freedom, so many ways that we can form a beam from an access point over here and another beam from an access point over somewhere else, and we can adjust these in phase so that they combine in a certain way and so forth. And this abundance of degrees of freedom that we have in the spatial beamforming also makes it possible to accurately null out the interference, and I think that's really a second thing here. I mean, it's a little bit like in conventional or co-located massive MIMO, right? One of the reasons that co-located cellular massive MIMO is so great is that we have a lot of spatial degrees of freedom to play with that can be used to null out the interference and so forth, and the same will go for modern DMIMO, where I mean, it's like a massive MIMO system. It's just that the antennas are spread out over a larger geographical area, so that, obviously the path gains or the path losses, I mean, from a terminal won't be the same, right? To different access points and so forth.
Yeah, and I think here you have one of the main differences then when it comes to coordinated multipoint, which was already introduced in 4G as the idea of having the conventional big base station and let the neighboring ones collaborate. But here the antennas are actually spread out. We don't start from a cellular network perspective. Okay, so if you want to find then what are the weaknesses, so what is the main challenges to make this actually be practical?
Yeah. Weakness, I don't quite see any, to be honest, really. Challenges, certainly. I mean, many of the challenges are on the implementation, right? How I actually build the electronics, which of course entails also challenges on the algorithmic level. Like now there's a lot of signal processing that will have to be done here. Where should the signal processing be performed, right? Should it be done at the actual access points or panels, or should it be done in some kind of central location? I mean, you could envision having very lightweight antenna panels, and then you have fiber optic cables and to some central processing unit, big as a fridge, where you have virtually unlimited with DSPs or other circuitry that can do the job. And on the algorithmic level, I mean, much of the challenge is like, so how do we distribute the signal processing without losing too much in performance or losing it all in performance? For example, if you want to compute the optimum, let's say zero forcing beamformer or MMSE beamformer, can this be done then by splitting the computational load over the access points in a reasonable way? And connected to that is also the issue of delays on or latency. Because if you distribute processing, then that means that maybe some access point has to finish a job and then forward his like data to the next access point, and that access point need to process his data and jointly with whatever he got from the other, and then forward to the next and so forth. And now if traffic is delay critical and you have 100 access points, then this might be a big deal, in fact. So that's certainly a challenge. I mean, just managing the complexity, right? I think another challenge is also on maintaining phase synchronicity. I mean, on uplink, that's not an issue, because on uplink you have two panels, even if they are out of phase relative to each other. The uplink data signal and the uplink pilot will undergo exactly the same phase rotation, but on downlink they have to be aligned in phase for joint beamforming to work. So protocols for that need to be developed. And what more? Energy efficiency, obviously, is a thing, right? I mean, we won't be willing to build, and maybe nobody will be willing to buy antenna panels that consume hundreds of watts of power, and we need to make sure that, I mean, they are power efficient or energy efficient, both when they operate at full speed, but also in idle mode. I mean, much of the time networks are likely to still be in idle mode, and you might have a few terminals that wake up now and then just to send a few bits, and then you don't want the network components themselves to just go idle and burn a lot of electricity. So yeah. These are algorithmic and electronics challenges to a large extent. I'm sure I missed a lot of other
I guess one more practical concern could of course be that you would like to have antennas everywhere ideally, but it's costly and it is something that might be hard from a practical perspective. Who owns things, who should put up the equipment and all these type of things. But I think I agree that this might be one of the closest things to materialize among the things we should talk about.
Yeah, indeed. I think, I mean, you're touching upon like challenges here that are more connected to regulatory constraints and
ownership of equipment
and for ownership. I mean, who's gonna put this panel up there, and where's the cable to it going to be hidden, and so forth, and who will pay for the I don't know, whoever needs to actually go there, right, and install it. But those are really not technological challenges. I mean, there's nothing in the laws of nature here that are against us and then we need to fight, right? It's more like a matter of deciding and establishing the right and the appropriate regulatory frameworks, I think.
Yeah, so we will eventually take steps in that direction, at least.
Yeah. So...
yeah, should we take the next one, perhaps?
Maybe we should. So why don't we stay with, let's say, maybe something closely related to MIMO, but still different from MIMO, right? So reconfigurable intelligent surfaces, Emil, or I think RIS or RIS, I think.
Yeah, I think people say often RIS now. Then it's also the Intelligent Reflecting Surfaces name, IRS. Then IRS is also a tax office in the US, so I think RIS sounds better to a lot of people.
So RIS stands for Reconfigurable Intelligent Surfaces, but IRS stands for Intelligent Reflecting Surfaces. Is that right? Because I thought that in the early days, I mean, when this vision was like emerged and people talked about reflecting the wave, but then more and more folks realized that, well, these small surfaces aren't really going to reflect, they will more like scatter, and therefore it's better to call it reconfigurable. I don't really know.
Yeah, I think that also comes down to semantics, in the sense that I think the word reflection, there is also, you can call it diffuse reflection and specular reflection, absolutely, and then everything is reflection. So
yeah, absolutely, it's a form of, I mean, if you think of a small metallic plate or like an atom in this RIS surface, then what it does is like diffractive reflection or scattering, right? But it's not like it's hardly a mirror. I think that's the point.
Yeah, but
is this 6G RIS?
So I think the best selling point of this technology is the following: that so we have built systems in the past that are designing the transmitter and the receiver very nicely. Now we have MIMO arrays at transmitter, and at the receiver we can do all of the cool things. We have abundance of spectrum and things like that. But in between them there is the rest of the world, and we need to sort of do the best out of that is given to us. And now the idea is that what if we put up equipment that gives us some kind of controllability of the propagation environment. If we then start looking at, you have the protocol stack with layer 1 being the physical layer 2 being the medium access and so on, then maybe there is something on layer 0 below the physical world that you can control and engineer, and that will then provide us with a new design dimension that we haven't.
That's a fascinating thought, but I mean, a more basic question here is like, so why don't we consider this when we choose building, like construction materials for buildings, right? I mean, rather than having, covering the walls with, or building walls from like reinforced concrete or something, we would like embed some other metallic kind of structure or something that would like scatter or reflect the waves in such a way that the radio propagation in the room. I'm not saying this is even possible, but I mean the way of thinking, right?
Yeah, I mean, we are doing this all the time. I mean, I'm sitting here in a room with white walls. But why do we have white walls? Because it reflects the sunlight or the other light in a better way, so it looks brighter. And the same kind of thing, of course, you can choose how you are painting things, what material you're using. We are already selecting where we put up base stations to get good coverage, but that is sort of design of the layer 0, so to say, before we are using the network. But configuring things online, that is sort of the new thing. And then the idea is then, okay, you need to have some equipment that can do this. So you put up this RIS, and maybe the simplest way of viewing it is that, I brought with me a small piece of aluminium here. And
foil, wow.
Of course, aluminum foil here will reflect the light, and if you are rotating it, the light will be reflected in different ways. And what you also can do is you can bend it, and then you will reflect in other ways. And sort of if something is bended, well, then you can focus signals at a particular point instead of reflecting in a particular direction, for example, or scattering, whatever we want to call it. Then what is a RIS doing? Well, it do exactly the same thing. It's just that it's electronic, so you not bend the surface, you just change its properties at some smaller level, so it's not homogeneous anymore, it's heterogeneous, so that way you control it. I think there's a lot of work showing now that, okay, we can do this. So
yeah, it's a cool technology. I mean, my reservation is rather that now the reconfigurability itself will require considerable amounts of like electronics that will have to be powered and built and so forth. And now if we're gonna build all this electronics, deploy it and power it through the grid, why not just put up a small access point or something else instead, right?
Yeah, and I think this is sort of one of the main concerns here, that okay, we get this new design dimension. That is cool from an engineering perspective. What should we use it for? And then if we are focusing on power boosting the received signal, then, as you were saying, there are alternative technologies, relays, small cells, other kinds of things you could put up. And in many cases, if you are, for example, transmitting a millimeter wave signal along a street, and then there is a cross-section, and you want the signal to enter into the neighboring street or perpendicular one, well, then a reflecting surface could help you with that, but it doesn't necessarily need to be reconfigurable because the street is still there.
But then we're back where we started, right? Where I suggested you could just put up some small pieces of aluminum foil at random to improve, just like you have a light-colored wallpaper because you like the room to be brighter.
So I think there people have been focusing a lot on this research in recent years. Some of the first big papers have more than 1,000 citations, and I feel that we are sometimes getting stuck into that this is only about power boosting signals or making smaller changes. I think we need to think more about what could we do that would be more fundamentally different, and then there is still a lot to be done around that to really prove that there are good use cases for this new design dimension. One thing might be that we would try to, if you have a MIMO transmitter and MIMO receiver, there are many cases where you observe more signal dimensions than the actual strong paths of your channel. So can you use these surfaces to add new strong paths that you are tweaking so that they become really distinguishable? And there could be other things like dealing with fading by making the channel get hardened to some extent, or you can try to hide Doppler effects, and so there are some more deeper kind of changes you can do to the channels, for example.
Yeah, but at the same time, I mean, rather than building a RIS of some certain size like this with small atoms or whatever, I mean, there's nothing in principle that prevents you from distributing these small atoms and just putting small scattering objects all over the place, and those could be just fixed up there, or they could be reconfigurable in some way. So I'm not saying there would be necessarily any, or even conceivably any advantage to doing it, but one could distribute the atoms in a RIS and just have small, possibly or potentially controllable scatterers placed all over the space also.
Yeah, and of course it's one thing that you can control them. That's the next thing you need to have a means of doing it. And for doing that, you probably need to have an RF chain there so that you can talk to it from a base station, tell, please change the configuration. And then all of a sudden, it is there is an RF chain plus a big surface.
Yeah. plus electronics to power the whole thing. So then, why don't you just put a small relay up there?
So I think that is why what the relay will do is primarily to boost power. So that's why I think we need to look beyond that and search for those type of use cases for this to be truly useful.
Yeah, but a relay, a distributed MIMO relay could also improve the rank of the channel, right? So, and that's indeed a technology that maybe we won't talk about today, but which isn't really conceptually new at all, but which people haven't talked so much about maybe for the last years. But distributed MIMO relaying could really be also something to look at more in detail, I think. Of course, the challenge there is like the phase sync and all that, but maybe that's something we say for the future.
Yeah.
So there's a final, there's one use case for RIS that I find rather compelling, though, potentially, and that is as a way of building a MIMO transmitter. Like, rather than building like a massive MIMO array or panel, you'd build a single antenna RF transmitter, and then you would put it in the near field of a RIS and use the RIS to control. Of course, you could only serve a single spatial stream or terminal at the same time, right? But you could steer the beam maybe by controlling the weights, which is an advanced form of what was known as a parasitic antenna many years ago.
Yeah.
So it isn't like a new thing really, but maybe the technology development that has happened in the field of RIS in the last years could facilitate building that type of transmitters. I would imagine that could be really useful at especially high frequency bands, right, where it's hard to build coherent MIMO arrays.
Exactly, and there I think there are much more commercialized kind of solutions. I'm not sure if they are separated like that, or if it's like it's more like a meta surface with a transmitter at the backside of a surface. But there are the companies. Pivotal Comware have something they call holographic beamforming, which is a solution built a little bit like that. I think there is QMeta that's building some kind of satellite transceivers. I think the more challenging part of the cases is when you have this big separation between the transmitter and surface. So I guess one of the features of RIS compared to many types of relays is what we call the full duplex operation. It transmits and receives the signals or retransmits at the same time. So let's shift over to full duplex communications in general. What is this? Is this a big new thing?
Yeah, full duplex is kind of a fascinating thing, right? You'd build a just radio transceiver that could transmit and receive at the same time. So then the question is, how is this accomplished? Well, with a single antenna, it could be accomplished. You need a circulator that splits the outgoing wave from the incoming wave and so forth. Or you could have a configuration with two antennas very closely located to one another and use one to transmit and the other to receive. In either case, you'd on the receive path get substantial self-interference from the transmitted wave, which needs to be cancelled. And there's technology for this. It's quite fascinating, right? This is analog filters and stuff that can be used, but also digital processing circuits that can essentially, it's like an echo canceller, but you need a very high dynamic range in the circuitry here, because you could have like that the self-interference would be so much stronger than the incoming wave that you're really interested in. So you need enormously high dynamic range. I think a combination of both here. You need also digital cancellation techniques that deal with residuals. So it's a fascinating technology, and I think from a 6G perspective, the question is really like, now, supposedly we could build, and we can build, folks have demonstrated this in labs, right? But supposedly we could build this like at a reasonable cost and so forth, and would it be useful to have in 6G like access points? And in a way, I think the answer would be yes, because this is a thought experiment. Suppose we could get this for free, right? Yeah, so it's nice to have. Look, we have full duplex, maybe we can do something useful with it, and maybe in the first generation of the product it'll just sit there as unused, but then there'll be a software update suddenly where somebody figures out a good way of like using it. So certainly it's a fascinating thing, I believe, but in the end, the question is also how much could one eventually gain? It isn't so obvious. I mean, now if you transmit and receive at the same time, as opposed or compared to as a regular TDD, transmit, listen or receive, transmit, receive, and so forth. And with full duplex, if you transmit all the time, you would like emit twice as much interference under a peak power constraint, at least. What are the consequences of that in a system perspective? I don't know.
I guess you can ideally double the data rate, assuming that you need the same data in the uplink and the downlink.
Yeah, in principle, but what happens to interference and so forth, right? I mean,
so this is sometimes my concern here. If I understood it correctly, because of being able to cancel interference, you need to have a few antennas for transmit and a few antennas for receive. So if you sort of double the number of antennas to double the data rate minus interference, you could perhaps double the data rate with those two antennas, but do some MIMO stuff.
Yeah, so it's like, I mean, we got an antenna here and we run TDD, so transmit, receive, right? Okay, so now let's make this full duplex. Now we might need another antenna that one that transmits and one that receives, and then we have two antennas. So the baseline for comparison is no longer the nominal system with a single antenna, but it's rather a MIMO system with two antennas in TDD, right? Which we know can be used to beamform and so forth. So I guess I have to really pass on the question as to whether there are any compelling system studies that show appreciable gains here, assuming, say, that state-of-the-art technology, which is now available and built in prototype form in the lab, could be commercially deployed on a wide scale at low cost. I do think there is one really exciting use case, though, which is uniquely facilitated by full duplex, if it could be built and deployed. And that is, if you think of reciprocity-based beamforming in TDD, right? The way that works is that terminals and access points take turns, right? So terminal transmits on uplink, pilots and data, and then the access point beamforms back on downlink. But when beamforming back on downlink, then the access point will use channel state information, which was learned from the uplink pilots. And those pilots came a little while ago, like half a slot back or so in time. But with full duplex, it could in principle be possible for the terminal to transmit uplink pilots simultaneously as the downlink beamforming is taking place, so that channel state information is not even slightly outdated, or at least less outdated than in traditional TDD. So that I feel like is a really exciting thing that could be a deal breaker. I mean, in high mobility, high carriers, right? So,
yeah, and I guess my suggestion there with you can double number of antennas to double the data rate. What that really entails is that you would probably need to double the number of users that you're serving. So it might be more relevant if you have a large number of users compared to if you really want to increase the data rate for one device. Then this is sort of one of the ways of actually sending twice the number of signals back and forth to it. Yeah.
Yes. Yeah. All right. So where do we go next, Emil? We did have a couple of more topics, I think, on the list that we had planned to talk about. And maybe the next one is joint communications and sensing, which is, I think, is fair to say, a fairly large and, as it seems to me, growing topic of research. So what is this all about?
So in a way, the communication and sensing in the terms of like localization of objects or radar, things like this. These have been two different types of systems that have been developed alongside and shared a lot of kind of ideas. So I mean, from the multi-antenna perspective, I think a lot of the people that started to work in that with communication came up with the ideas from radar community, for example. And when we are now sort of motivated by communications of building these advanced systems, they have a lot of antennas, so they can resolve signals in angles or different directions, whatever way we do it. We have a lot of spectrum, which is sort of making it possible to sample signals quickly and see small changes. We have a wavelength that becomes shorter and shorter, and that also gives us a better kind of resolution. So then I think the general thought there is that, well, if we are building these systems anyway for communications, can't we use it also to sense our environment? And what would that be? Well, it could just sense that things are moving around, someone's coming close to a base station, or localize objects, or do all kinds of sensing tasks.
But that's clear, right? I mean, just the sheer amount of baseband data that we have with all these MIMO arrays and so forth, that all the data could be used for something else than only communicating. I mean, since this is already out there, right? I mean, for example, classical example is to use Wi-Fi, or rather the impulse responses measured by the Wi-Fi access points to sense whether something is going on. Are there people in the room? Has somebody fallen on the floor, or something like that happen, right? So granted, now with all this baseband data that will be available from all these MIMO arrays and so forth, then that data could also be used for inference about what's going on in the environment. But I thought that the notion of joint sensing communication is rather like a way of looking at, so how could we design like waveforms that carry information but at the same time are also useful for active sensing of the environment, so that an access point would act not only to communicate with terminals but also as a radar, more or less. Is that a correct understanding of what this joint sensing and communication
this
means?
Is sort of what the research then is going towards. So if you sort of come for free that we could use the communication infrastructure also for sensing, then what kind of changes should we do to how we're operating it in order to do the sensing better and better? And I think an important thing there to bear in mind is that there are fundamental differences from what kind of waveforms we would like to have in communications and sensing. So in communication, we want them to sort of be bandwidth efficient. We try to sort of use something that resembles sync pulses in the time domain, which spreads out a lot in time, so that they are very confined in frequency. While in a sensing systems, you prefer to have something that have very narrow time dimensions, so you can send a pulse, it bounces off an object, and then you can see precisely when it comes back, because the pulse is very short, and that then spreads out a lot in frequency. So that is sort of showing why different types of waveforms are generally preferred for communication and sensing.
Yeah, but I thought that a signal used for communications should in general look like white noise, more or less, right? Isn't that what you get? I mean, if you take a message and you encode it using a random channel code and so modulate it and so forth, and you get something that resembles white noise. If you look at the spectrum, it's kind of like even the power spectral density is evenly or almost constant over frequency, right? You want to spread over as large a bandwidth as possible, I think, because bandwidth is always more worth than power in communications, right? So a signal which is good for communications should look like white noise and be spread over a large bandwidth, I would argue. And then we know from radar or time delay estimation that a signal which is good for like range estimation, well, it should have a peaky autocorrelation function, which means that its spectrum should be also flat. And the width of the peak in the time domain is inversely proportional to the bandwidth. So it does seem to me that signals that are good for communications are also good for at least for ranging and or for range estimation and vice versa. But then, of course, you could argue like in the spatial domain that maybe a signal That's good for communications. Well, that should be directed towards the receiver, right? Using some beamforming, whereas a signal used to sense the environment maybe should be more omnidirectional or should explore some part of the space where we have less information and so on. So I can absolutely see that there is a trade-off involved here.
I mean, the general thing there is that, okay, you have a transmitter sending out the signal bounces off of different objects, and then you have a receiver that picks up the signal. And in the monostatic mode, this is sort of the same location, and then maybe you're using full duplex as you were talking about before, or in the bistatic case, the transmitter and receiver are different arrays at different locations. And then from the communication perspective, sort of you estimate a channel, and the important thing is that you estimate your channel taps, and you don't care about if these were multiple objects or not, or whether your sort of pulse shape to use is mixing up different types of multipaths or not. Well, for the sensing, you will like to be able to separate them better and better, and that then you want to get more semantics out of the channel and not only measure the components of it.
Yeah, right. I can, of course, also see that there are system optimization aspects here. Like, well, suppose there's some base or some access point wants to sense very accurately the environment, and there might be an advantage to other access points in the vicinity to shut down temporarily to not create any interference at all. I mean, in communications, very often we can bear with the interference. It's just there, right? And we adapt our modulation and coding and so forth to live with it. But maybe with sensing, if you really want some high resolution data, then it's like, yeah, now it's my turn to sense. Please be silent for a millisecond or something. So certainly I can absolutely see there are many new problems here to address. And
and then there are a few different aspects to this. To on the one hand, it's sort of okay, it comes for free that we can do some sensing as well. Then, to some extent we can already do sensing with the sensors we have, and you were mentioning that it can already be done. So I think some of the effort is sort of, should we change our standards in order to make the sensing perform better? And then if we do that, then is this something that will only be used by the network operator to improve its own service inside its network, or is it meant to sell other types of services to try to monetize it? And if that is the goal, then we have this general problem that most of the time when network operators try to control what services people are using, in the end it's some over-the-top service that is winning the game, like Google or Apple or Facebook or someone. And
indeed. I mean, the equipment is already there, right? So now we got these MIMO panels, then, well, it's neat. We can use them to beamform and communicate and all that, but indeed we could also use them as a bistatic radar and we get that capability for free, right? And for one thing, we could reuse just the baseband data from the communication link to make inference about the environment, but we could also design radar-like signals designed to probe the environment actively, and again, the equipment is already there, so this functionality would be an extra piece of software and algorithms, more or less. Yeah, it's a cool prospect, I think.
Then a final non-technical thing is also that if people that are not understanding wireless technology very much are already concerned about radiations levels and privacy and these type of things, then if we start to say, oh, now we have a network that can sense everything, they are essentially spying on what you're doing, they know where you are, then that could also sort of be another kind of issue.
I certainly think it is an issue, and let's not underestimate the amount of information that's contained in all these baseband data. Just the channel impulse responses, they tell a lot about who is at home in the house, what are they doing, who is maybe on the street or something like that. So maybe that's a topic we should return to at some point.
Yeah, no, exactly. Even if you are making sure the data as such is very well have good privacy through coding, then you can still find other information about you. Okay, so maybe we should take the last thing we were going to talk about. So orbital angular momentum, or OAM. What is that?
Orbital angular momentum. Wow. Okay, so where do we start? Is this 6G? Probably not. But let's see what we can say about it.
Yeah,
so,
I think there's some people who really say this is such a new dimension for 6G. So I'm curious to hear your take.
Yeah, so my take is that there was a lot of buzz about orbital angular momentum, or OAM, I think about 10 years ago. And when you read papers, and you'll see claims like, well, this is a new type of radio technology that generates helical wave fronts or phase fronts, and that have a singularity along the axial direction and so forth. And when you just look at this, it's like, wow, here is something new that we haven't understood. What is it? I mean, I'll tell you, the first time I was exposed to it, I was like, wow, what is this? This is a kind of new quantum phenomenon or something that we just haven't captured before, right? I mean, I was living like in the world of Maxwell's equations, where we have electric magnetic field, and then we have these different modes of propagation in a waveguide, and we have these different like polarizations in free space and all that. But it's certainly not. I mean, and this is well known and understood by now, despite the buzz that was there like 10 years ago. And it was really a buzz, I mean, in the scientific literature. There was a buzz about it, and there was in the media also. The BBC made a story, I think entitled something like "Twisted Radio Waves Will Boost Capacity of Wireless Communications" and so forth. But the thing is that OAM is nothing else than conventional point-to-point MIMO, or rather what you get with conventional point-to-point MIMO when you have accurate enough channel state information at the transmitter, so that you can do the textbook stuff, I mean the SVD or water filling, like beamforming and all that. There is nothing here that goes even an inch beyond, I mean, classical electromagnetics. And this is important to understand, I think. And I have to tell you that, you look at, because there are some papers in physics, right? Physical, I think, review letters, that very highly cited papers. And I kind of got a little bit of a hit down here, because I used to think, I mean, granted, there's a lot of nonsense, unfortunately, published in IEEE journals, right? But I used to think that, like, physics, that's natural science, is so clean that, I mean, these papers are like of a different like level somehow. But then you see this kind of things, and then you really kind of changes your worldview almost a little bit. So I think the short answer is there's nothing new here at all. This is point-to-point MIMO, properly optimized, and this is well understood. I mean, there's a paper that I can warmly recommend by a colleague over Edforce with a co-author. I can't remember his name.
Yeah, we can share it in the description of this episode.
That neatly outlines more technically what I just now said, right? And I think it's important for people to understand that there's really nothing here. I mean, in terms of, well, there are certainly questions in terms of, let's do point-to-point MIMO. How do we best optimize the geometry of the array, right? I mean, there's no reason why a MIMO array should be uniform linear with half a wavelength spacing, or rectangular with half a wavelength spacing, or anything like that. This is just a gross misconception that, well, it's easy to do some of the math in free space line of sight, so you find it in textbooks, but there is no reason in practice why it would look like that, indeed. So certainly, I mean, the array geometry and topology could be optimized using proper electromagnetic models. But once that's been done, and once we have everything on the standard form, the standard model, and we account for mutual coupling, and so far that's a significant effect, and so on, and we make sure to get channel state information where we need it accurately enough, then OAM is just an instance of point-to-point MIMO.
Yeah. So my take on this is sort of that, okay, if you take two arrays of antennas, they probably can have any shape of them, and then you put them very far from each other in free space, then there will only be one way of transmitting that reaches them, and that is then this textbook kind of beam. Then you move them closer to each other, and you are coming closer than the Fraunhofer distance, and so you're in the radiative near field, and now you can all of a sudden transmit multiple signals between them in the point-to-point mode, and then the geometry of the arrays determines how those signals actually look like. And from a communication perspective, it doesn't matter.
If you look at OAM, if you look at the literature on OAM, you'll find illustrations, very beautiful color picture of beam patterns, right? It looks like exotic flowers or something, and these are, entirely accurate. This is what you get with point-to-point MIMO.
Yeah.
Once you're in the near field of your array, and once the array isn't any longer like lambda half spaced, uniform and linear and so forth.
Yeah,
so
I think in OAM they are using circular arrays that they are pointing towards each other, and then you happen to get this kind of beam shape, so it's not really beams anymore. And if you take some other structure...
that can be debated. What does a beam mean, right? But if a beam means something shaped like some kind of oval, or then, but certainly you get radiation patterns, right? And you can compute them and you can optimize them, and this really
and with the same number of antennas as you would need in OEM, you can put them in another way. You will be able to get the same capacity. It just will look different physically.
yeah, exactly like that. So
okay, so then we have addressed that point as well.
We did. Okay. So I think we did cover the 6
we covered all of them.
trends, not all. We covered, let's say, 6 of these, all the 6G technologies and trends that are out there, right? And that was a fun discussion, Emil.
Yeah, and I think when we were preparing, we were having a few more ideas, but that wasn't 6 more. So if anyone who is listening have ideas about things they think we should talk about in the same kind of way, then we'd be happy to get your suggestions. So please comment on the YouTube version of this podcast.
Oh, absolutely. As always, we always welcome comments and questions on the podcast. So. Good, Emil. Done.
Yeah.
See you next time.
Yes. Have a nice day.